Yes, I guess so. So last time we did go through the basic function analysis, and I gave this following subtask. These were not mandatory, but for practical thing. So let's go on the second slides over here. So it was quite simple, just making a new directory and searching data and copying data to the directory and doing some elementary basic filtering and other kind of application routines that you get familiar with how the platform is functioning. So let's go first through those. So first of all, here is again the main screen. Right. So now we are in. So the task was first to make directory and rename it on today's date, and then use search tool to find how many episodes contains those different data types. And then it was to be chosen one particular episode, the USCP, and make subfolder into that directory what you just have made with the date and name it with the episode name. And of course, it's good to know that what is the episode all about. So hopefully you have read that, and then copy those files in that directory. Afterwards, it was supposed to filter the catalog to have the more or less 10 largest events on that particular catalog, and rename the output catalog as you please. And then using one of the events, and not events, picking one of the events from the catalog and retrieve the corresponding seismic waveform in the seed format. And then again, use one application to convert this seed format signal to the mini seed format. So that's about it. So first of all, first one was to make the folder. So it was simply by clicking either from here or from actions to make the directory. Giving the name, I will give today's date. Example like that one. And then you have the new folder down here. I will just move it here for the convenient. So it's empty. So that was the first part. And then it was supposed to search for those certain data types. And it's done from here, from this multiplication class. And since we ask particular data types, so we can filter them out. It was catalog. I think it was velocity model, and it was ray tracing angles. Those three. I will just double check that. No, that's already next week's assignment, and yes, those three. So then we just search, and since every episode does have the catalog, we can see that there's catalog for each one of the episodes, but there's not necessarily velocity model and the ray tracing angles from every place. So it is safe to assume that the catalog is actually existing, so we can take that out. Now, all right. Then we can use these headers here to list them alphabetically. And we can see that there is ray tracing angles for 6 different episodes. And there is much more of velocity model available for many more episodes. For instance, Pyhäsalmi mine does have a catalog and velocity model, but doesn't have the ray tracing angles. And about the files themselves, you can look information from the user guide or the documents. But yes, there's now total of 6 different episodes that contain all of these 3 different data types. So the answer for the first question was 6. And then I asked you to have particularly one certain episode to look in the USCB, which is here in the first one, to have all of those. So we can filter this more, so we can filter by the episode itself. So we can go here and select the, where's that one? Here, like that. And also because we want to have the catalog, we can go and right-click it here and search. So here are the 3 ASCII files. And we could have done already the one subfolder for the date file, but let's first copy these 3 to the workspace. And after clicking all the 3 ones, you can just add them at the selected the workspace button over here, and not as link, but at the workspace. So it's actually copying them there. And this is the date file, and I will just copy them there like that. Note that when you are moving not one but several files, it doesn't have this show button over here, which is highlighted when the operation is done. If we select one file like this and using this at the workspace, then it would show it. So it shows a little differently, but they are there. My workspace, and then you can see that under the date files, the files are there now. And it was also asked to make subfolder here with the name of the episode. So when we are looking the workspace tree, we now click this date folder here or directory and make a new directory, which comes always under the folder that you have selected. So this was USCB, I guess. Something like that. And you note that these are going under this the parent folder here. And then it was just to ask to move these 3 files to that. And you can do it by dragging, clicking like here. And you can see that you need to open this folder by clicking that. So now this folder is open. So then you can just see that it's that little symbol over there. It's actually moving a little bit on the right. So then it's under that folder. So now we have here all the files in the right directory. Then it was supposed to filter the 10 largest events from this episode, USCB. And now there's 2 ways to do it. You can go either to the applications and find the filtering application, or you can go directly on this catalog file. And first of all, you can click the catalog and it opens the catalog view in the workspace. But there is another option, then go and click the actions here. And this action over here is the action for the file. And this action below, this is action for the file itself. It means that the content file actions are listed here and the actions for the file itself are here. So you can see that the applications clicked here, actions clicked here is the same that if you click it, these 3 dots right next to it. So I'm not going to fetch the application from the applications listing, but I'm going to use this in application, this particular file, which shows all these available applications, taking this as an input, as told last time. And let's go into catalog filter. So when clicking this, it always makes this new application just below the input file. And since we particularly use this file in these applications, it's already puts it there as an input file. Then we just need to filter it out. Because I asked the largest events, it's maybe a good idea to see the actual content of the catalog, that how large events they are. So I'm again selected the catalog, and now I'm going to this action list and look the catalog preview. And from catalog preview, we have these all parameters associated for each of the events. And in this episode and this catalog, the magnitude column is this local magnitude ML at the end. And by clicking the header, we can put them in either, it depends, in the alphabetical order, or then we can have them in this largest to smallest or smallest to largest values. And now it shows the first of the list is the largest one. So we can actually look at what is the magnitude range if we want to have around 10 events. Of course, we could just pick all those different numbers here and take the 10 largest, but I think it's more or less to have roughly the 10. So if we look down here, so 3.8, I think there's 8 of the largest events. So I think we need to have the events larger than 3.7 to have actually 10 events in our filtering procedure. Taking that away and going back to the application itself. Now we find the correct parameter and select by range. And as we just looked at, it was 3.7 magnitude to the maximum. And then we can just run this. And after the run, the outputs file is going to be shown here below the application. And it shows that with this parameter range, we had 13 largest events from this particular catalog. And the map here is showing where they are. So it's quite a large area already. And if we now look to workspace 3, we see that the catalog is here and it was asked to rename it. And we can either select the catalog mat here, the file, and use this action or this 3-dot action button here. Let's use this time. So we can find that there is this rename. And we can name it, for instance, as we have filtered it. it's sometimes a good idea to name the files what you have done it, so it's quite more clear to you what has been done for the file. So here we have that. Now, next step was to loop one event. Yes, these have been filtered now, and now it was supposed to select one of the events from that filtered catalog and retrieve the corresponding seismic waveform in seed format. So let's do that. So we can chain this the files in this workspace tree, and again we can just select now the new catalog, what we renamed, and again click here or the actions here and have the using application. And now there is this signal download tool, and let's click that. So the signal download tool just downloads the waveform from this what are being connected to this catalog. And the selection is quite easy. First we select what event waveforms we want by selecting them from the catalog. And since we only have these 13 events, so it's pretty much easy to pick from these largest ones. So I will take the number 6, for instance, and click OK. And it was asked the seed signal, so there is not other but the seed signal, but I'll just tag the seed signal here anyhow, because some of the events episodes does have seed signal and accelerometer seed signal, which is a little bit different data format. And then we just run it. So it produces 2 files. One is this seismic event file .json and the USB signal with ID and then the seed, and they are just below this one. And furthermore, it was asked to find a suitable application to transform this seed signal. If opened, it looks like this. So it does have the seismic network information as well, what you can see from here. That there is the stations that have been used in this and their information as well, and just and the waveforms itself. So let's find suitable application. Again, clicking here, and this doesn't have actually too much of different kind of applications to use. So it was asked to translate the seed to mini seed converter. So this looks suitable for here. When you click it, it automatically retrieves the applications just below this input file and puts the input file here as an input. And this doesn't have too much to done. It just changes a single seed waveform to the mini seed. So we just run it. And after that, we have the mini seed signal over here. And if we open that one, you can see that this mini seed format, it actually is a mini, as said in the format type. It only has the waveforms. It doesn't have the information about the network itself anymore, which you can see that the map is not seen here. All of these waveforms does, however, have the information about what is the station. It's written in the format, but it doesn't have all the information from the network itself, what kind of sensors it has, and so on. All right, so that's about that. And now we don't have too much time, so let's go let's go forward with the single event analysis. And as you have seen in the lectures, that the single event. Yeah.
I'm sorry, did I actually got lost when we created the micro seed?
Yeah.
So we were supposed to be on the seed, on the initial.
Yep.
Yeah, is it? I actually, or I do have that folder, but not the one that's below.
Oh, that one.
That one, I don't. It doesn't create for me.
Let's see.
Because,
go on.
I'm sorry. That what I understood, we have to create it from here. From using application C to insert converter.
Yeah.
Correct. And it generates like another folder that it does have.
Yeah, you need to run it.
Oh.
Yeah, because all the applications need to be run. They are not automatical in that sense. So yeah, now.
Oh, yeah.
Yeah, yeah. It's sometimes some of the applications could be that if you are using them in this kind of, it's only doing that. So it kind of could be a nice idea to that it actually changes it automatically, but it doesn't. You have to press the run.
Thank you.
Yeah, so it's quite a hierarchical routine on that one.
Yeah.
So, okay, so the single event analysis. So, what does it tell us? Why do we do any single event analysis or multi-event analysis? For first of all, the single event, of course, it tells about the event itself. It tells that how it occurred and where it did happen and what kind of properties we can pull out of that. And that's why single events are, particularly those what are quite large, they are very, very detailedly analyzed by modeling or localization and looking at the spectral analysis. And today we are going quite quickly through two of those localization algorithm, what we have the application localization and the application called spectral analysis in this platform. So let's continue with this same episode what we just retrieved, so we don't have to use time for retrieving another episode or data sets. You will have some subtasks for this anyway, so you're going to make this yourself. So as I already took that sixth, if we look the filtered catalog here, and if we look the catalog itself, I took this number 6 here, and now we have the data over here. So if we wouldn't have that catalog, we only would have these waveforms in the seed format or mini seed format, and we know the station locations, and we know the time, and we know how the wave have come from the event. So we have recognized that there is actually a seismic event happened somewhere, but it needs to be located. There is this application called localization over here. We could go there directly, and we will, but I will go first in the applications just to look at the content of that. So I went to the applications, and since I know the name of the application, I just can put the name over here, and it just gives the list of those which has a name or meta file, something called localization. So this is the applications we're going to use. And there's a description that how it is working. It's based on this Tremor localization software, which has been now implemented in this platform. So the author is Fujin Debsi from the IT Pass. Last update is around 6 years ago. and the directory name which we are having in this workspace is called localization. But this also gives some general information about the input file. So this is actually saying that this would need to have the seed waveform, but I tested it and it actually wants the mini seed format. And also it wants to have the catalog, seismic event ID, or the seismic event file. This is the JSON file, what we just had. And then it wants to have this multi-seismogram peaks, you will see soon it, and the velocity model. And then it gives the posteriority probability density distributions, residual data, some logging file, and extracted relocalization event properties. But we will see those soon. So now I'm going to add this from here to workspace. And let's get all the way down to that one. So let's put it in the seed to mini seed, since we have this mini seed formatted file in this folder. And you see it's down here. So despite the description page, it actually wants a mini seed format. It doesn't eat the seed format, which I found a little bit strange, because this wants to have the network inventory, which are combined into seed format. But this is how we are going. So we still need to retrieve this network inventory file from the USB-C episode. And let's do that first here. So let's go to the episodes. Actually, we can go, yeah, let's go to episodes. And we can just find the correct episode from the list, or you can use the filtering. I think it's actually on the last page. Yeah, here. And from here we can go to there's actually two of these networks, but we are using this seismic network over here. This motion network is a network of the ground motion observations, not the seismic observations network. So let's click that one. It opens it. So it shows all the stations that are associated with this episode there at the Poland. And with the action button over here, we can add this to the workspace, and let's just put it all the way down. Actually, I think we can put it in the seed to mini seed. So just upload that localization. Great. And now you can see that there is this show briefly. So I'm just clicking it. So it automatically goes to the moved file. But we want to work now with the localization here. So with the localization, we now need to put all the input parameters here. So first of all, the mini seed waveform, which can be seen, I think, yes. Now that we open the seed to mini seed, so we can find it from here. It doesn't even show the other files. It only shows those files that file formats that are suitable for here. Clicking OK, then the just copied network inventory, which we can find again under that one. And this is typed with XML. If you would download this file, you can open and see that it's actually this kind of internet format. How many of the network are in this? I think the name now escaped me about this format, but it's very typical in the seismic handling and the description of the networks. So we click it, then it wants to have the catalog, so we can use that filtered catalog, and it is that one. Okay, and the last one is the velocity model, which we already copied in the subtask 1, and it's over here under the USCB episode folder. All right, now we have all the input files here, and next thing for the localization, that how this application is actually working, that it is based on the picking of the first arrivals. The first arrival, what is arriving first from a seismic event or an earthquake to the seismic station is always this this P wave, and we can zoom in the first part of the event, and we will see here that the signal is more or less stable in the beginning, and then there's some waves are arriving from the seismic event, so it's starting to observe the motion in the ground. And we can zoom in, and we can see that there is this static noise that's quite small, but this event, I think it was magnitude of 4, so it's quite large. So it's no wonder that this static noise is very low comparing the event motion to get motion. So in this localization, we just need to pick out the first arrival, what is just point, and we can only pick here the P wave. In some more advanced localization routines, you can also utilize the S wave if you can recognize it, but in this one we only use the P wave. So for the P wave, we just have it now selected here automatically, and we just trying to recognize where's the first arrival is here. So somewhere there. So you can see that it actually the motion is starting to rise over here, but it's usually best not to take just here, but a little bit after, and usually use the same point of the phase in all the stations. Since we are now dealing with quite large seismic array, so that there's many kilometers between those stations, it's not that vital to have it here or here. But in smaller arrays, such as Pyhäsalmi, where the stations are only a few hundred meters away, it's more important to have more accurate. And in order to do that, it's better to have a same kind of spot if you can recognize it. Okay, that was the first station. And this particular event actually has data only for 4 stations, which is quite low. So again, zoom in by dragging. This is a little bit more difficult. As you can see that this is noise before the event arrival, but then something is happening. So where to pick? So sometimes it's very difficult to recognize where is the actual first arrival, and this can be due to geology, or it can be due to diffraction of the waves, so that it's coming from multiple directions at the same time. So the end result can be something like this. So it's very hard to say, but in this case, I would say it's somewhere here. It's already doubles the amplitude versus the prior, and I think that this is too late already over here, so it's somewhere here. That's my initial guess. The second guess is comes after we have made the first analysis. But now let's take that one and zoom in. And again, I think it's here. And the fourth one, zoom in, and we can actually use this application magnifier here. And I would say that it's this one. Even though it's not that clear, but it's not because this is a real data, it doesn't necessarily be as a some book example quantity, but it's a real. So what else does this applicator wants? It wants to have the event coordinates, which we can get from the file, which means the catalog. Yeah, actually wants has to take that. No. This file is actually, this is now that file, JSON. So either we could use the catalog for this one, or we could use the event, seismic event file, which came on the same time when we download signal. So these have the basic metadata I discussed last time. So let's click that. So it just takes the coordinates from that, because the localization wants to have the coordinates of the original event. We could just put there something. It's kind of an initial guess or something.
I'm sorry, after you selected with the keywords, you went to load value from file?
These ones?
Oh, yeah, no, after that.
Yeah.
I already did that. Then you needed to load value from file?
Yeah.
And what file did you choose? Sorry?
I chose that event file, which can be found from, we have this signal download tool, which gets the waveforms. But beside the waveform, it actually forms this seismic event.json file. And this just has the information about the basic information about the event, that, the location. Like that. Yeah. Then we have some parameters here, what we should be going through a little bit. So this a priori variance, it's just these are the parameters that you can actually read yourself from the user guide or the application guide. But bottom line here is that this kind of determines that how much it's actually trying to put in the initial x, y, and the depth coordinate what it's going to solve, because this is an iterative motion. So it's kind of trying to several station places where what fits best for the observations. That means the distance from the stations to the possible event location, and it also utilized this seismic event seismic velocity model, which gives the information about how fast the P wave is moving in the subsurface. In this case, you can look it yourself, but it's 1D, so it just increases with depth. It means that where the depth is, it's actually giving it a little bit more faster than in the shallow. It depends a little bit how it's formed, but it's quite simple. Then there's something norming, but we can just use these default settings here. And then there's some likelihood variances what we could change. Then there's minimum and maximum value for the depth, so we can control the modeling or tracking the localization a little bit. And then because this is iterative motion, so we have this kind of this step values, that how much in meters the solution is going to change it between those iterations. Of course, you can't see those, all of those, and these are the basic parameters for this localization. There is also advanced options, but I don't think that we are going to need those in this course. So if we just use these default settings and run, it takes a little bit of time. All right. So this output file shows it's kind of first calculates this maximum likelihood solution, which is giving in the latitude and longitude, and also some value for the depth. Then based on that, it also gives this average solution based on all those iterations what it's done. and what is the latitude and longitude, and how much is in meters is the error margins. So error margins are something like 300 meters, which are quite large if you think about the micro scale. But if we look our seismic stations over here, they are quite, this didn't show those, but it's quite a many kilometers between the stations. And we need to remember that we only have 4 stations in the particular event. So this shows our stations, and here it gives 3 bubbles, which are our solutions. The solutions, the blue one is this maximum likelihood solution, and the average solution is green one. And the original event, it actually that event location from the catalog. So although it utilizes it in somehow, it kind of for the educational purpose gives you the idea that how well you picked your first arrivals. And you can see that there's a little bit difference there, not too much if you think about it. I personally don't like that they are mixing up the latitude and longitudinal degrees as a place, and then they gave some error margin in meters. It just doesn't make sense to me, because it's really difficult to say that how many meters nowadays difference between these two. You can check it if you want. And the other one here is this localization event depth. So it kind of gives that how depth was this localization done. So the original one was just determined that it's in 1 kilometer. And our solution gives 900 meters, and the average solutions with the error margins, which are these bars over here, by average it's almost 1 kilometer. So that was pretty good picking. And then it produces some additional results, like log of the localization, output, residual, and XCP. I don't remember what that was, but all of these are in text formats, and if you click those, it opens them here.
So during that, so you see all of the things that we did, it was we pretty much like we localized where was like where it's like the epicenter of those seismic events.
Yes.
Yeah.
Okay. Yeah. Epicenter and hypocenter as well. So it kind of shows you, of course, the XY location, and also you can have the third dimension as well. Yeah, this shows the epicenter or the likelihood solution for that. And this average solution, usually, if you get those error margins smaller, then it kind of says that the picking is fine and the velocity model is okay, that you can use it to describe it. But all of these event locations in the catalog, I think that for this particular episode, they have been localized using this software. So you should be getting it more or less there where it should be. All right, so time flies so fast. So another applications what I can show you very briefly, but it's a little bit more easy to put with, is this spectral analysis. And we can just use the same signal tool here. So this mini-seed, sorry, it's over here. This mini-seed file, what we just used in this localization. So clicking here and using application, and this time you can see that now we have this mini-seed, we have much more of different kind of applications usable than when we have the seed file. So now let's go to the spectral analysis and select that one. And for spectral analysis, we also need to have a almost the same input files. So we need to network inventory,
Okay. So, oh,
network inventory, which we had. So let's go this here. So it's the same file we used in the previous application, and the velocity model as well, which should be just under the episode folder like that. And you see this load picks from file. This means that you could actually do the picking in with the different applications, which gives the output as the picks. So you don't have to use them in this application, in the spectral or localization application itself, or you can even save your picks for the further use. Sometimes it's very good idea to save the picks and then just go and fix them a little bit. But anyway, so these applications, if you don't change it, they stores the picks or faces. Just as the tip. So the spectral analysis. So we could go and look the application space and look the material from there. But I think that you can do it yourself. The bottom line in this, how this is working, is that again, we will choose the file, and this time we are not picking a point, but we are picking a page, which means that we want to know that where we can recognize the P wave when it's arriving. And in this case, I would say that the P wave, the first arrival was there, but the phase for the spectral analysis, we want to know more than just that one point. We need to pick how the P wave is actually performing and how it's behaving during when it arrives. So we can have the spectral content. So in this case, we select this area, for instance, from here. And this time we can also, I will zoom a little bit down, we can actually pick the phase of the S wave as well. It's very difficult to say that where the S wave actually comes from, but it's very safe to assume that this is already a signal from the S wave. So first I just change this P to S. And every time if you want to delete something, you can just select the phase or point, in this case phase, select the P and clicking the X, so it removes that if you want to do it again. So now I selected phases for the P and for the S wave. For practical reasons, I tend to put them in separate places that they are not overlapping. It's okay that if they overlap. Sometimes it's very difficult to see that where the P wave is actually ending and where the S is starting. So you can have the margins, because the spectrum analysis is going to look all the content from that one. It doesn't harm if they are a little bit overlapping. But this time I'm just putting like that. And this could be done on every single station here. And you can see that there's actually information from all three components here. And I did take the jet component here, so we can take these horizontal components away and just look these four signals over here. So then when we could now pick the second phase from another waveform, but let's just use the one, because this only requires one. We can always analyze one or two or all of the stations, and then it calculates some fitting based on all of those, which is better. But now, just for the sake of the functionality of the application, let's just use that one. Again, this one's the event coordinates, and it is that same .json file, what we just used in the localization, just under the signal download tool. Let's select that. It gets the coordinates, and this actually doesn't want to have any other information. You just run it. And as an output, it gives you two figures. The first figure over here is that the spectral analysis of the B wave phase. So the phase, okay, that phase. And this darker blue color here is the fit, as it's trying to make it into this snow fit. I'm not going into details on that how it's working, but it's kind of trying to determine the corner frequency based on this observation. The corner frequency is that when it's starting to fade this main amplitudes of the spectrum. And this has the amplitude of the spectrum, and here is the frequency. So it has this kind of fit, and based on this fit and its relations to other seismic parameters, it had derived some parameters from this event. So this particular event should have the source radius about 200 meters, which makes sense because this was quite large event. It was something magnitude 4 or so. It calculates seismic moment, energy or released energy, and the stress drop on the bedrock. Also, it gives some apparent stress over here. And then it gives the slip, which is, I think this is something like 16 centimeters. So it means that the rock mass has moved about that amount of distance in the soil, which is 16 centimeters. Of course, it doesn't sound too big, but we have to understand that a lot of rock there, so it produces quite a large energy release already. And this actually calculates the moment magnitude, which is 3.1. It's less than what the follower from the catalog. I think it was 4.0. We can check that by clicking that filtered catalog and going in the catalog preview. 3.7. Okay, it wasn't 4, but so it's closer. So, oops. Let's go back to spectral analysis. Yes. So here is that image. So this is based on how the B wave is forming, what kind of information the B wave is bringing from the seismic event to the station. And the other one is based on the S wave. And this is the S wave parameter. So as you can see that by the estimation of the S wave, the radius is much smaller and the magnitude is much smaller. So I would say that my S wave pick wasn't that great. So I should go and take those away. I can go there and just redo that one. Of course, if we wouldn't know that what the magnitude is, then this is crucial. But for now, in the sake of education, we can always compare it on this catalog value. In order to make this solution more stable, we should do this for each station. And let's just do that quickly. So first of all, the B wave phase starts somewhere. We can always take a little bit of this background noise in the beginning and then click it like that. And for the S wave, let's start from there and go all the way there. As you can see that this is not as, I would say that this is not as clean data than from that station. For the first station, oops, where did it go? For this first station, we have this. Guess that is a little bit slower today. We can recognize the P wave, the S wave, and the surface waves quite easily. But the other stations or some stations, it's not actually that clear, and that's a relation about how good the station has been installed, where its locations, and what is the gear geology. But now we have selected 2 ones, and all these files are already there, so we can just run it again. So this time we have picket phases from P phase and S wave for 2 stations. And it's still calculating. So yeah, now we have these 2 stations over here. That was the first one, and this is the other one. And for both of them, this corner frequency fitting has been done, or snow fitting. And since we have this fits, we have now this. There was only one of the stations in the previous time, but it kind of have this spectral level with this meters times time, and also the corner frequency, what it can be found from these 2 stations. And based on those, it kind of gives us another preview. And this time you can see that this is going, well, it's quite still large, but the moment magnitude has gone much smaller. So this is just estimating the source parameters, how it's done in seismics. But that was for the P wave, and for the S wave, we can have something similar. I actually think that the fit is quite nice. It goes more or less there, but this is always the thing that the parameters may not be as exactly the same from the and this is moment magnitude. The magnitude what was in the catalog was a local magnitude, so the scaling might be a little bit different, but still they should be more or less near to each other. So when you are doing this, and if you are doing several different stations or events which are more or less in the same magnitude range than each other, and your solution should be relatively the same for the catalog. I would say go to this catalog still like that, and show you, yes, the catalog, okay, like that. So if we have here those 4.1 and then 3.7 and 3.8, so the analysis from your spectral analysis should be the same order, that the largest one is the largest in this catalog as well. So because it's a different scaling. But this was the basic functionality of the seismic spectral analysis, and there's actually quite nice video. At least I found it, and the user guide is quite nice as well. So you should use that when you're trying to reproduce this. We are way over time already, but yeah, I'm going to put today's lecture video online today, and also I'm going to put this subtask 2 in the Moodle as well. And in this subtask 2, you will do the localization tool, use it, and also the spectral analysis. And as a bonus, there's one more application you can try by yourself, and it is this Foggy. And this was done to analyze the focal mechanical solutions. So I gave you some tips here, but next Monday, we are going to go through an example of this. But it's a very good idea to you to get familiar and see how this application is working. You can, if you get it working and you can get some results, you can then look for your lecture and see that can you determine how the rock movement have been occurred and so on. But the thing is that I'm most probably going to put the focal mechanism into practical work. So best to get yourself familiar with the application. The input files are not that more difficult, and in that case, you just have to pick again a phase, but look for the instructions, especially on that user guide. What is that? What is that phase for? It's not the same kind of phasing than in the spectral analysis, but it's just showing that which way the first arrival is coming. But we will look at next time. Yeah, do you